Okay, today we're going to look at section 2.3. We're going to talk about functions. A function is a relationship between two things. It's a rule that assigns to each element of the domain exactly one element of the range. The domain is the set of all inputs, independent variables. We usually use X for the domain. The range is the set of all outputs or dependent variables, usually Y or the function notation f of X. So for each input, there can only be one output. A function may be defined by a set of ordered pairs, a table, a graph, or an equation. So the following table gives y as a function of x, y is equal to g of x. So our domain and our range. Our domain is simply the x values. -4, -1, 0, 1, 3, 7, and 12. Our range is our y values or our g of x values. 5, 7, 3, 15, 8, 9, and 10. So why is this relationship describes y as a function of x? Well, because y is the dependent variable. Y, to get y, we have to input x. And essentially for every value in the domain, there is exactly one value in the range. I think that's what we're looking for there. So let's decide these sets of ordered pairs define a function. Okay, so let's see. I have the x value of 1, gives me a value of 3. That's one value. I have an x value of -2, gives me a value of 4, one value. I have an x value of 3, gives me a value of 5, again, one value. Now this is the tricky part. This says that every value in the domain or every x has exactly one y. It doesn't say that every y has exactly one x. So this is okay. This would be a function. Be careful of that. Now again, let's look here. Is this a function? 2 gives me 3. 3 gives me 2. That's fine. 4 gives me 5, and 5 gives me 4. Yes, this is a function. Okay, what about this one? 3 gives me 4. -2 gives me 5. 4 gives me 6. 3 gives me 6. So looking at this and this, I have two values, two different y values for the x value of 3. So not a function. So determining the domain and range looking at a graph. So remember, domain is the x values, range is the y values. Now, it took me a long time to realize there's an easy way to remember that. Alphabetically, domain comes before range. Alphabetically, x comes before y. So looking at this, keeping in mind that this goes on and on forever. This goes on and on forever. So looking at my domain, what are my possible values of x? Now looking here, this keeps going this way forever. So I would think negative infinity. Same here, this goes this way forever. Positive infinity. How about my range though? What is the lowest value for y? That's going to be this point down here, -5. Now -5 is part of the domain. So again, we use brackets like we learned. And it goes upward forever, so that's to infinity. Likewise, let's look here. We'll start with the domain. The lowest x value is this -3 here, and it is the point on there. So we use a bracket and it goes on to infinity. And our range, well, our lowest value is 0. And the 0 is part of it. And again, this goes up forever as well. So infinity. Okay, let's see what we have next. Determine if the graph is a graph of a function. To do this, we use something called the vertical line test. If each vertical line intersects the graph and at most one point, then the graph is that of a function. So we're talking vertical lines. This is a function. However, this would not be a function. Now, if you have a graph, you can look at it and tell, typically. Determine if an equation defines a function. So we need to determine if for each x there is only one y. And we do that, solve each for y. So this one's solved for y. What do you think? For every value of x, do I get a distinct y? Yes, so this is a function. Essentially, a linear equation is always a function. Now let's look at this one. Well, we want to solve for y. Y equals 5 minus x squared. Now, for each value of x, and we're going to get one value of y. I'd say let's look at this here. Think about x equals, let's just use -2. X equals -2, we have 5 minus -2 squared, which is 1. What about x equals 2? We would have y equals 5 minus 2 squared, which is 1. So what is that telling us? That's telling us that I have 1y for 2 x's, but that's okay. So we're looking at a function here. So what about here? Let's just try. Let's do this way. It says to solve for y. What if we do this? X squared plus, or y squared plus 9 equals x. And what if I let y equal -2? I get -2 squared plus 9 equals x. I get 4 plus 9 equals x. I get x equals 13. Now, what if I use positive? Let y equal 2. In that case, I get 2 squared plus 9 equals x. 4 plus 9 equals x. X equals 13. So for x equals 13, I have 2 different y, so not a function. Again, just generally not a true look. This is a line. This is a parabola, which we'll learn about later. And this is like this. So you can, once you graph them, you can definitely see it. Okay, what about the domain for an equation? We need to look for any restrictions on x in the form of dividing by 0 or taking the square root of a negative number. So here's where we're at. We learned about I last chapter. At this point, we're talking about graphing. So we're only dealing with reals. We're using the rectangular coordinate plane. There is another plane that includes imaginary and combination complex numbers, but we're not using that. So for this, when we're graphing here, we're looking at just real numbers, no complex numbers. So we can't have the square root of something negative anymore. I know it can get confusing. So what do we got going on here? Look for any restrictions on x in the form of dividing by 0 or taking the square root. Well, here I'm not, so there are none. So my interval is simply negative infinity to infinity. Again, this is that shape. Now, what do I have going on here? Well, x minus 3 cannot equal 0. So x cannot equal 3. Now, the way to write this, we start at negative infinity and we go to 3. 3 is not included. So we union that with, again, 3 to infinity. This is how we show that it's all reals but 3. Or we could say, well, it says interval notation, so we'll do that. So here, we're looking at a square root. So that means that 7 minus 2x has to be greater than or equal to 0. So, what, add 2x to both sides, divide by 2. So x must be less than or equal to 7/2. So that means less than, which goes all the way to negative infinity, to 7/2. We have equal to, no bracket. Okay. So function notation is y equals f of x. So what we need to do here is solve for y. So if I take and subtract 16x from both sides, I have negative 4y equals 8 minus 16x. Divided by negative 4, I get y equals negative 2 plus 4x. Maybe we make that a little prettier and say 4x minus 2. Then we change it to f of x equals 4x minus 2. So now what we're talking about, this notation means for x, plug in negative 5, 10, a, x plus 1. So if my original equation is f of x, or function I should say, is 4x minus 2, then f of negative 5 is equal to 4 times negative 5 minus 2, negative 20 minus 2, negative 22. F of 10 would be 4 times 10 minus 2, 40 minus 2, which is 38. And we can put variables in there. F of a equals 4 times a minus 2, or 4a minus 2. And f of x plus 1 equals 4 times x plus 1 minus 2. 4x plus 4 minus 2, 4x plus 2. That's how that's done. Okay. Doing the same thing here. Negative 5, 10, a. Negative 5, 10, a, and x plus 1. So we have this in the right format. So we have f of x equals x squared minus 2x minus 3. So f of negative 5 equal to -5 squared minus 2 times -5 minus 3 is 25 plus 10 minus 3, which is 32. F of 10 is 10 squared minus 2 times 10 minus 3 is 100 minus 20 minus 3, which is 77. Likewise with the A, f of A is equal to A squared minus 2A minus 3, and f of x plus 1 equal to x plus 1 squared minus 2 times x plus 1 minus 3. So this is x squared plus 2x plus 1 minus 2x minus 2 minus 3. We have 1x squared, 2x minus 2x cancels. I have 1 minus 2, which is -1 minus 3 minus 4. And that is that. Okay, now we're talking about increasing, decreasing, and constant. Suppose a function f is defined over an interval I. If x1 and x2 are in I, f increases on I if whenever x1 is less than x2, f of x1 is less than f of x2. F decreases on I if whenever x1 is less than x2, f of x1 is greater than f of x2. And f is constant on I if for every x1 and x2, f of x1 equals x2. So we lost our functions here. Or did we? There they are. So let's see. Let's look at when these things change direction. There's this point here, and there's this point here. Now, how does this work? There's an easier way to remember this. Essentially, we're always going from left to right. As we go from left to right, as x increases, so think of it this way, as x increases, what happens to y? So let's start with this first one here. I'm way over here to the left. I'm actually at negative infinity. As I'm going from negative infinity and I get to this point where it changes direction, which is -1, as x increases, y is going down. So this is decreasing. Now I'm here at this -1. And as x increases, what's happening to y? And it's ending at 1. Well, as x increases, y decreases, or as x increases, y is increasing as well. And then starting here at 1 and going all the way to infinity, as x is moving this way, y is moving that way. So again, we have decreasing. So you're essentially looking at what is y doing when x increases. So let's look at this other one here. And this is not arrowed, so this stops here at -7 or -8, I'm guessing, and 8, yes. So it's stopping, it's not continuing on. So I'm starting at -8. And then to this point, there's not a change. So I'm talking -3, and what's happening? As x increases, y is constant. Now I'm at that -3, and my next change in direction is down here at 2. And what's happening to y as x increases? Y is decreasing. And here I am at this 2, and I'm going all the way to 8. And as x increases, y increases, so it's increasing. So those changing in directions, turning points, they're called. They're local extrema. A local minimum point is a point where the curve changes from decreasing to increasing. And a local maximum point is a point where the curve changes from increasing to decreasing. So find the maximum, find the minimum. So look, I'm increasing, then I'm decreasing. This point right here. This is a maximum. Now I'm decreasing, now I'm increasing. So this is a minimum. And what do we have? -1, 6, and 1, 2. Turning points. Yep, we got another one. Okay. So we're talking relative minimum, maximum. So I'm increasing, I'm increasing, I'm increasing. I get to this point, -1, 3. Now I'm decreasing. So this is a maximum, a relative maximum. Now I'm decreasing, decreasing. I get to this point, 0, 2. And now I'm increasing. So this is a minimum. Now I'm increasing, increasing, increasing. Then I get this point, 1, 3. And now I'm decreasing again. So that's a maximum. Essentially, we're talking an interval, a high point, an interval, the high point, interval, the low point. Again, in this class, you really don't need to know the full details of what it means by an interval other than just a section of the graph. If you go on to calculus, you'll get into much more detail of that. And that is all we have for this section.